Well, good morning, everyone. My name is Robert Scott, and I'm the Baywork president. And also, I work in technical training at Valley Water. Welcome with us today to the Baywork Training Buffet. We're glad you can join us. We'll be here. Hopefully, you are attending more than just today's session or this session, and you'll be joining other sessions as well. And we got a good slate of topics to be covering today, tomorrow, and the next day. So looking forward to that. I want to ask you to, if you can, type your job title and your organization into the chat so that we'll know who's in the room. And we have a wonderful presentation for you today entitled Aquatic Chemistry and Surface Water Quality. Mark Seelos will be giving it. He's an associate water resource specialist at Valley Water. So I'm gonna turn it over to Mark now. But also, if you have any questions, feel free to put your questions into the chat and we'll address them, as many of them as we can. Mark, I'll turn it over to you.
Awesome. Thanks, Robert. And thank you to Robert and Elizabeth for organizing this event and for inviting me along. Yeah, any chance I get, I'm happy to share my knowledge in aquatic chemistry. I feel like chemistry kind of gets a bad rap, especially if you've had to sit through high school chemistry. But hopefully by the end of today, you're convinced that chemistry is actually really fun and cool. And you'll see how water scientists kind of take almost a forensic investigation approach to identify and respond to water quality problems. And so we're going to start out with Water Chemistry 101. That's going to be the majority of the talk. And this is going to be kind of fun and interactive. And we're going to go through a water quality problem, a hypothetical situation, and how we would address it as water managers. And then for the next part, we're going to go through water quality regulations. And I'm going to give a special focus to the Clean Water Act, not just because that's the most important water quality regulation that we have to work with, but because we're celebrating its 50th birthday this year. And so I'm going to kind of show you guys what you should know at minimum working in the water industry with regards to the Clean Water Act. All right, so starting our scenario here. So imagine you're a water scientist and you get into the office on a Monday morning and you get this notification email with a picture taken by a community member that shows murky water in the creek behind their home. And so does anybody know what some possible causes to this would be? You could just drop it right in the chat. What could cause that murkiness?
Any thoughts, anyone?
Yep, sediment, yep, that's the main one. Sedimentation, yep, mud, rain, exactly. Yep, so that would be my first choice too. And so we head into the field to investigate. So we go into the creek behind the house and that stretch of Uvas Creek, and we measure our water quality vital signs. And so these are our most important water quality parameters that we think about. And they're called vital signs because it's almost like the heartbeat or the blood pressure of the water. So how these things are doing are going to affect all of the other water chemistry in the system and also all of the organisms that live in it. And so we're measuring temperature, dissolved oxygen, pH, conductivity, turbidity, and we're going to get a really good feel for what all those are today. But the thing that jumps out immediately is that the turbidity, which is a measure of how cloudy and murky the water is 135 NTUs. And so that is very, very high. And so now we want to find what's the source of that turbidity. And so we walk on that stream from the community member's home all the way up to the reservoir outlet, and we see that that whole stretch of creek is totally murky. And so we think it must be coming from the reservoir, right? But then when we get upstream to the reservoir, we see that it's perfectly clear and blue. And so we kind of have a little bit of a mystery on our hands. And the first thing we want to do as water scientists is produce a hypothesis. And so my first hypothesis would be, well, maybe we're mobilizing sediment, stirring it up from the bottom of the reservoir with the reservoir outflow, and that could cause that murkiness downstream. And so once we have that hypothesis, we need to find a way to test it. And we do that by collecting data. And so one of our most valuable tools that we have as water scientists are our water quality meters and our sondes. And so a sonde is an instrument like this one right here. I don't know if you can see my pointer, but it's the white in the picture. And it has a bunch of different probes that measure depth and all of our different water quality vital signs. And so what we want to do is go into the reservoir in that deepest spot, lower that sonde throughout the water column, and take measurements all the way up and down so we can see if we can identify that problem in the reservoir. And the first thing we're going to be looking at is temperature. And I'm going to show you guys a bunch of plots that look exactly like this. And you can kind of think of the boat floating on the top of the plot and the depth going all the way down to the bottom of the reservoir right here. And then the dots in the plot are going to show whatever value that I'm explaining, and that's going to be on the x-axis here. And so when we look at the temperature profile, we can see that the reservoir has separated into warm layers right up here, where it's about 25 degrees, and that's Celsius, and cold layers down here, where it's about 15 degrees. And so we can see this really distinct separation of temperature. We call that warm part the epilimnion, the bottom the hypolimnion, and the middle the thermocline. And so to understand why water separates into these different layers, we need to know a little bit about its structure. And you might remember from general chemistry that each individual element has a valence electron shell, and those electron shells participate in chemical bonding. And all elements want those outer valence electron shells full. That's when they're happiest and most stable. And so we know that oxygen has 6 valence electrons, but it wants 8. And hydrogen has 1 valence electron, but it wants 2. And so water arranges like this together to create this bent structure. And the reason why it's bent like this is because oxygen actually attracts the electrons a lot more than the hydrogen. And so it creates this uneven charge density where the oxygen side has a slightly negative charge and the hydrogen side has a slightly positive charge. And we call that polarity, or a polar structure. And so this polar structure that water has actually is responsible for the majority of its really interesting properties. And the reason is because these positively charged hydrogen sides and the negatively charged oxygen side stick together like magnets. And that actually causes things like this water beads on the top of vegetation that you can see, surface tension here, where you can see insects that walk on water. And it also contributes to water's relatively high boiling point because the individual molecules are stuck together. They don't want to be released. And it also contributes to the fact that water is called the universal solvent, which I'll go into later. But with regards to the separation of the reservoir into those 3 layers, the most important thing we have to know, other than the structure of water, is that temperature is really just a measure of motion. And so things that are moving really, really fast have a high temperature, and things that are moving not so fast have a low temperature. And one of the really interesting properties of water is that the higher the temperature is, the lower the density of water is. And so that epilimnion, that warm water that we saw on the top, actually floats on top of that cold water in the bottom because it's less dense. And so that's kind of what we were seeing when the reservoir separated into those 2 sections. And another thing that's really interesting about water and is really unique about water is that when it freezes, the density actually goes way, way, way down. And that's because when it freezes, water lines up like this into this crystal lattice structure that's actually less dense than water that's warmer. And so that is why ice floats on top of water. Okay, so getting back to our lake stratification. So you can imagine we're in the summer, our sun is beating down onto the reservoir surface, and that's causing this epilimnion to really warm up. And that's creating this density stratification where this warm layer on the top is floating on that bottom layer. And so that's what we saw before with that temperature profile. And you'll see that a lot of the other water quality parameters that I'm going to go over are intimately related to this temperature profile. And so you should really think about temperature as one of the most important things in water chemistry. Okay, so now next we're moving on to a different parameter that we measured with the sonde. So we're going to look at dissolved oxygen. And we have the same kind of plot here. And the temperature is shown in this darker blue. And something that really jumps out at you is that this dissolved oxygen profile mirrors the temperature profile. So you can see you have high dissolved oxygen in the surface waters of the epilimnion. And then once you get into the thermocline down here, it really starts to drop off. And by the time you get into the hypolimnion, that cold, dense bottom water, you actually have 0 dissolved oxygen. So there's no oxygen, no fish can live down there. And so to understand what's happening here with that low dissolved oxygen in the bottom, we first have to kind of understand how gases dissolve in the water. And gases dissolve in water by Henry's law. You might remember it from general chemistry. And it's a super, super easy thing to remember because there are only 2 variables. So the concentration of gas in the water, that is dissolved oxygen in our case, is related to the pressure of the gas in the overlying air. And so if you have a higher concentration of oxygen in the air, you're going to have a higher concentration of oxygen in the water. And this K right here, this is called the Henry's law constant. And that is basically just related to how soluble the gas is in water under a given temperature. And so this is going to be different for all the different temperatures and all of the different gases that we're working with. But one of the really interesting things about Henry's law is that we can actually calculate how much oxygen we should have in our water given a temperature. And so I went ahead and did that here. So we know the composition of the Earth's atmosphere. So it's 21% oxygen. So therefore we have 0.21 atmospheres of oxygen. And we're just going to multiply that by the Henry's law constant for oxygen at that temperature, which has been determined experimentally. These are all available online. And then we can just convert that to our mass units that we're familiar to be looking at and see that at 10 degrees Celsius, oxygen can hold 8.74 milligrams per liter of oxygen. And this is an important number to know because we know that if our concentration is higher than this, then there's something adding extra oxygen. And if the concentration is lower, then something's taken away oxygen. And so going back to our reservoir, I'm going to just briefly explain how reservoirs get oxygen so that I can explain why we had that anoxic low oxygen layer in the hypolimnion that we observed. So like I said, reservoirs get oxygen from the atmosphere, and that dissolves based on Henry's law. But we can also get oxygen put into the reservoir from photosynthesis. So another interesting thing is that CO2 from the atmosphere dissolves into the water, and that CO2 can be used by algae and plants, and they basically use that for photosynthesis, and the byproduct of that is oxygen. And so a lot of the time, if you have over 100% saturation of oxygen in the water, it's because you have all that extra input coming in from photosynthesis. But oxygen isn't just added to reservoirs, you can actually have oxygen taken away. And the main thing that takes oxygen away from reservoirs are bacteria, like this little green guy down here. And so bacteria basically breathe, they do respiration in the same way that we do. And so they break down organic matter or food, and they do that using oxygen, and they're releasing or exhaling CO2. And so how much oxygen you have in your reservoir at any given time, or your creek or stream for that matter, is a balance between how much respiration is happening and how much photosynthesis is happening. Those are the main things that are going to control your oxygen in the reservoirs. So what can happen is when our reservoirs are thermally stratified, like we mentioned before, based on that temperature profile, basically that top layer, that epilimnion, is completely blocked off from the bottom layer. And so what that does is it prevents oxygen from entering into the bottom water during those periods. And so you kind of have a limited pool of oxygen in the bottom here under stratification. And the bacteria, they're still going to keep eating. So they're going to use up all that oxygen and produce CO2. And that's going to lead to low oxygen conditions at the bottom. And that's exactly what we saw. So that low oxygen that we saw in that previous temperature profile is from bacteria consuming all the oxygen at the bottom. All right. The next thing we're going to look at is pH. And I'm showing you the same profile again. Again, the blue is the temperature profile. And you can see that the pH actually also mirrors that temperature. So it's really interesting. And you might know pH is like a measure of acidity, how sour something is. You might know that like lemon juice is low pH, and things like bleach are high pH. And pH stands for the power of hydrogen, and it's considered one of the two master variables in aquatic systems. And the reason it's called a master variable is because the pH actually dictates all of the other chemical reactions that can occur. And so it's really, really important in our natural waters. And pH is calculated as the negative log of the concentration of H+. I'm going to go on to that in the next slide, and hopefully by the end of this, you'll know exactly what we're talking about when we talk about pH. And so key to pH is the fact that water can what we call self-ionize. And so you can have water molecules that basically rearrange their hydrogens, and you can have, instead of H2O, you can have H3O, and you can have this OH form. And water does do this, but in really, really, really low concentrations. And so you might have, 10 to the -7 moles per liter of your hydronium ion, that's that H3O, and 10 to the -7 moles of your hydroxide. And that's a really, really extremely low concentration in the water. And so basically pH is just the balance between how much of this H3O you have versus how much of the OH you have. If there's more H3O, your pH goes down. If there's more OH minus, your pH goes up. And that's kind of what you can see with this equilibrium equation right here. I don't want to go too much into this, but you can basically see that when both of your H3O and OH right here are the same value, then that is when you have a neutral pH of 7. And so if you have a lot more of your H3O, then you're going to have a lower pH. And if you have a lot more of your hydroxide, your OH minus, you're going to have a higher pH. And so in our reservoir, we have a lot of things that are affecting pH. So first of all, the natural pH of the reservoir is kind of set by the local geology. Like if you have different carbonate rocks or different rocks that can buffer the pH, you'll have kind of different kind of standards for each reservoir, depending on what watershed you're working on. But also that microbial respiration that I was mentioning earlier can actually affect pH. And that's because when oxygen is taken up by microbes, then they actually release CO2 that can react with the water here, and it can basically release H plus or that H3O into the water. And so that's effectively raising the concentration of that hydronium, and that is going to cause your pH to go down. And so basically when we saw that pH drop in the bottom waters before, then that's just an indication of this microbial activity. Okay, so now we're going to move on to conductivity. And conductivity is basically a measure of the concentrations of ions or electrolytes in the water. And so really, really salty water will have really high conductivity, and water that's really, really pure and not very salty will have low conductivity. And we could see something interesting here. Again, here's your temperature profile. And you can see the conductivity profile is basically the opposite of the temperature profile right here. And so it's really high at the bottom and it's relatively low at the top. And so immediately we should be thinking, okay, what's going on down here that's causing that to go up? And as I mentioned before, water is known as the universal solvent. So it can actually dissolve more things than any other substance. And it's called the universal solvent, and it has this unique property because of its polar structure, actually. And so what can happen is when you put salts like sodium chloride or other salts into water, you can actually have the water molecules break apart that salt, and they actually form these what are called hydrated ions. And so when you have a positively charged ion like sodium, then all of the negatively charged oxygens on the water line up to that to basically neutralize the charge there. And then when you have a negatively charged ion like chloride, all the positively charged hydrogens line up to that. And so these are called solvated or hydrated ions. And these are actually a lot more solid or a lot more stable than the solid form of the salt. And so that's basically why salts dissolve in water. And so conductivity is actually really easy to measure because all you need is a voltage source. And so when you measure conductivity, you're measuring the rate at which electricity is conducted across the water. And so if you have a lot of ions in your water, you're going to have a lot higher conductivity. If you have lower ion concentrations, it's not going to conduct as well. And if you're familiar with Ohm's law, so V equals IR, then conductivity is just the inverse of the resistance. All right, so got a little chat question here. So if you were to throw a blow dryer into this deionized water bath while you were in it, then what would happen? Anyone have any ideas? So yeah, you'd be fine. And yeah, that's true. A lot of people think, well, water conducts electricity, so you'd be electrocuted. And that's not so true, actually. So the ions are actually what's conducting the electricity. And so if you were able to completely remove all of the ions from the water, it actually doesn't conduct that well. And so that's kind of a interesting fact there. All right. And so now I'm going to go ahead and try to explain why we had that really high conductivity at the bottom. And again, these pesky little bacteria are to blame. And so what can happen is under zero oxygen conditions, after all of the oxygen is used up, bacteria actually turn to other sorts of oxidizing agents that they can use to break down that organic matter and get their energy. And so these are all called anaerobic bacteria. And they can use things like manganese oxides and sulfate and iron oxides. And as a byproduct, instead of releasing CO2 only, they're also releasing these metals that are dissolved in the water, and sometimes sulfide and ammonia. And so since these are all charged here, they're actually increasing the conductivity in the bottom water. And so that inverse profile that we saw for conductivity with the really high values in the bottom are due to all these bacteria that are releasing all these charged species. Okay, so now we're going to move on to the actual parameter that we were concerned about in the first place, and that is turbidity. And so you can see the turbidity here in red, and it really increases when we get to the thermocline. That's probably because we have algae that kind of get stuck in there. And since algae are particles, they're going to cause some cloudiness. But then we can see at the bottom of the reservoir, the turbidity is actually really low, even lower than the top. And so that's kind of weird because our reservoir releases from the bottom. And so if all that murkiness in the creek was coming from the reservoir, we should see really, really murky conditions in the bottom, but instead they're really, really clear. And so, yeah, like I said, turbidity is just a measure of clarity. And there are a lot of different things that can contribute to differences in turbidity. So you can have particulate matter in the water. You can have sediment, like we mentioned earlier. You can have algae. You can even have colored dissolved compounds, like dissolved organic matter, that can contribute to turbidity. And there are a lot of different effects that turbidity can have. It can affect fish spawning. So fish actually can't have too much sediment in the system because their eggs will get covered, and that'll affect their reproduction. Some fish are visual hunters. So if the water's too murky, they can't see. Sediment can also carry pollutants that often stick to solids. And then obviously, if you've ever worked in water treatment, you know that it can complicate drinking water treatment. And so I would say that based on our turbidity measurements, we kind of have a bit of a mystery on our hands because we weren't able to pinpoint the cause of the turbidity to the reservoir. And so since we still don't really have an explanation of where that murkiness is coming from, we're going to do some additional analysis and just take some water samples to analyze for all of our major cation concentrations, our anions, some of the major things that we look at in water. And we're going to do that both in the reservoir bottom and at the outlet. And so now I'm going to go ahead and compare some of our results. Imagine we get these results back on Rush, and I'm comparing values taken at the reservoir bottom to those downstream values. And so the first thing I notice is the temperature is the same in both. That's what we'd expect because the water from the bottom is going straight downstream. But then I notice, so we have that 0 dissolved oxygen in the reservoir bottom, and downstream we have 10.1 milligrams per liter. And so that water is getting released from the bottom and getting really rapidly oxygenated. And that is being accompanied with this drop in pH. So there's a difference there. That's kind of implying that something chemical is going on, some kind of chemical reaction. And then we can see conductivity, it decreases a lot from 450 to about 150. So the ion concentration goes way down, and at the same time, our turbidity goes way up. So to me, that's thinking, maybe something is precipitating. So something that's dissolved in the water could be precipitating out and forming a solid. We look at manganese, and that's about the same in both places, but we notice that iron goes from 40 milligrams per liter, really high at the reservoir bottom, to 0 downstream immediately. And so now we're going to revise our conceptual model here based on the information that we've gathered. And so what I think is happening here is that under those stratified conditions where we have that temperature thermal stratification, we have 0 oxygen conditions at the bottom because all the oxygen gets used up by the microbes. And then once those microbes use up all the oxygen, we get our anaerobic bacteria that are releasing iron into the bottom water. So those would be called iron reducing bacteria. And the thing is that iron isn't really stable in the presence of oxygen, this iron 2. And when it goes out of the reservoir outlet and gets exposed to the oxygen, then that immediately gets oxidized and it precipitates with hydroxide. So that forms this solid, this kind of yellowish brownish solid that we saw. And that actually sucks up the hydroxide, which is increasing the relative concentration of the H+. So that's causing our pH to drop. And so that is just an example of how we can use kind of the detective approach, knowing what we know about all of our major water quality vital signs to solve a water quality problem. And so now that we know that this is happening, we need a solution, right? And so one of the main things to consider, like I mentioned before, is that this iron release can only happen under 0 oxygen conditions because these bacteria can't live when there's oxygen. And so the obvious answer would be to just add oxygen. And there are a lot of different oxygenation systems that you can use that can basically help you maintain those high oxygen concentrations in the bottom to avoid those anaerobic bacterial processes that can contribute to water quality problems. Another thing you could do is just cap the sediment with an amendment, maybe activated carbon, that sucks up this iron too. So instead of it being released into the water and downstream, it would stay bound to the sediment right here and just cycle back and forth with the changing stratification throughout the seasons. Cool. All right, so that goes through the first, that was just a brief primer on all of our major water quality parameters and how we use them as water scientists. This would be a good time to take any questions if you have any questions about that. And if not, I can move on to surface water quality regulations. And then,
any questions, anyone, or comments? You can unmute yourself if you like. or type them into the chat. I know Mark has covered a lot of material, but he's trying to build a case here and tell this story. Any comments or questions? We have a question here, Mark. Do you see it?
Yeah, I see it. With iron produced red water. Yeah, iron precipitating usually makes kind of like reddish, orangish, yellowish, brownish water. And that's actually, it's not the water, it's the actual iron oxide particles that are in the water. And but exactly what color it is kind of depends on what form of the iron has precipitated out. Cool. All right, so I think with that, I'll move on to the Clean Water Act. And yeah, so like I said, I wanted to really emphasize the Clean Water Act here because it's the most important regulation that we work with regards to surface water quality. And we're celebrating its 50-year birthday today, so this is a good way to celebrate it by raising awareness.
Mark, before you go on, it looks like there's another question in the chat from Minerva. Did you already answer? Did you respond to that one?
Yeah, so that's
Okay.
yeah, so that's interesting. So this is a question about ferric chloride in clarifiers producing algae blooms. And yeah, so I think the thing that this is, the question that this is getting to is that iron 2, that same kind of iron that we were talking about before that was released from the reservoir, is actually an important micronutrient for certain cyanobacteria species. And so potentially, if you had more iron 2, you could have increased algae blooms or primary productivity. And that is something that I don't know if I've really addressed that directly to clarifiers. I think that would be more something that would be in the bay. So because if you were using ferric chloride in like wastewater treatment process, then you might have increased iron concentrations in your effluent that could potentially stimulate algae blooms in the bay. But that's a good point. Yeah, anything that we do can affect water chemistry or potentially biological productivity downstream. But my agency actually, we don't work on the wastewater side. We work on the raw water and environmental side. Cool. And so, yeah, moving on to the Clean Water Act here. I'm going to start out with a national call to action. And so you might have seen these photos before. And this was really the beginning of the clean water movement when the Cuyahoga River in Ohio caught fire. And these photos gained national attention. They were published in Time magazine and National Geographic. And this really spearheaded the environmental movement throughout the country. And so just starting out with another question here, you can just drop it in the chat. What year did the Cuyahoga River catch fire? (1952), that's correct. 1969, that's also correct. Does anybody have another guess? Can I get a 1912? Also correct. Yep. And yeah, it's crazy. So it's all of them. And actually, it caught fire at least 13 times in the 1900s. And the reason why I did it is because it was basically receiving raw industrial waste and effluents from all different kinds of industries. And so you had all this oil and fuel that was floating in the river, and it was actually causing the river to catch fire. And so this had been happening for a while, but really increased news coverage on these kinds of things is really what spearheaded the clean water movement. And we started seeing all of these different headlines throughout the 50s and 60s about polluted rivers, about fish kills, about industrial discharges, and about untreated wastewater discharges. And so as a response to this, people rose up and joined together in defense of their clean water, began to lobby Congress, and actually created Earth Day, the first Earth Day. And that was in 1970. And so following this uproar, we actually got the Clean Water Act is what came out of that. But we've had a couple key federal and state water regulations throughout history. On the federal side, the first real major Water Pollution Control Act was in 1948. This was the Water Pollution Control Act. And this actually wasn't as effective as it could have been because it only applied to interstate waters, so waters that went from one state to another. And so that left the vast majority of our water bodies without jurisdiction under that law. In California, we really got ahead of the curve by passing the Dickey Water Pollution Act in 1949. And that's actually what established our State Water Resources Control Board and the 9 regional boards, which I'll go over in a little bit. However, they didn't have that much authority under that act. And what really solidified the regulatory authority of the water boards was the Porter-Cologne Act in 1969. This is known as the California Water Code. And this is used as the basis of a lot of the water quality regulatory actions that happen in California. Following that, that was actually timed perfectly to make the State Water Board an effective enforcer of the Clean Water Act in 1972. And the Clean Water Act basically began with a really heavy wastewater discharge focus. And it evolved in 1977. It adopted the National Pollutant Discharge Elimination System program, which I'll go over in a bit. And then in 1987, that program was expanded to include stormwater, which is now a really big deal, especially in an urbanized area like the Bay Area. Okay, so the California water boards really serve as the both state and federal nexus with regards to water regulation in California. And they're responsible for kind of 3 main areas. So water quality is one, water rights is another, and drinking water is the third. And so I'm going to really focus on water quality right now because this presentation is about surface water quality. And the water board, so the State Water Resources Control Board is actually managed in a network of regional water quality control boards. You're probably familiar with Region 2 here, and that's the San Francisco Bay Regional Water Quality Control Board. And what those regional boards do is that they enforce the Porter-Cologne Act and the Clean Water Act. And the main planning tool that they use to do this are called these basin plans. So each of these different regions is a hydrologic basin, and they each have a basin plan which basically sets water quality standards and designates beneficial uses for water bodies, and also creates basically an implementation plan for how we can implement both the Porter-Cologne Act and the Clean Water Act. And so, yeah, you should definitely take a look at the basin plan for the San Francisco Bay. And so I'm going to go over implementation of the Clean Water Act in 3 parts. And the 3, it's a really, really long law. And so you'd probably be bored to death reading the entire thing. But there are 3 sections or titles that are really relevant to people who work in the water industry. And Title 2 is regarding grants for treatment plant construction. Title 3 sets standards and the enforcement of those standards. And Title 4 is related to the permits and licenses that are required under the Clean Water Act. Okay, so Title 2, this is one of the first things that the Clean Water Act did, and it had a really, really huge positive influence on our watersheds, on the Bay. And the key thing here is that prior to the Clean Water Act, we had a lot of these minimally treated or untreated wastewater and sewage discharges that just went straight into the creeks, straight into the Bay. And so what would happen is that wastewater would go straight into the Bay. And since it has so much carbon in it from all of our everything that's in that, it would actually be quickly consumed by bacteria in the Bay, and they would take away the oxygen when they would do that. And so you can see here on the right, in the 1960s, you can see that we had dissolved oxygen concentrations below Dumbarton Bridge in the San Francisco Bay, dropping to 0. And that's just totally crazy when you think about it, that our bay that we look at every day could be 0 oxygen. And that would cause things like harmful algal blooms and fish kills. And the bay was really just a really gross thing at that time. And then you can see that with the implementation of the Clean Water Act, that actually created what are called technology-based standards. So it required things like clarification and secondary treatment, things like that. And pretty much right when that was created, we saw this big increase in dissolved oxygen concentrations in the bay. And then further in the 1990s, the wastewater plants actually conducted upgrades that allowed them to remove even more of the biological oxygen demand. And now, oops, sorry about that. Now we actually rarely drop below 5 milligrams per liter in the bay. And so this program, Title II, funding for treatment plant construction, has really been a huge, huge success story in the bay. And you can see that again down here with where you're looking at the biological oxygen demand load to the bay. Pretty much right when the Clean Water Act was passed, you saw it drop really dramatically. It continues to drop to this day. Okay, so for section 2, we're going to go over water quality standards. And so, or sorry, for Title III. And so Title III sets water quality standards in a 2-step process. And so first, each water body in a basin, in the basin plan, is assigned beneficial uses. And so these beneficial uses are potential current or future uses of the water body. And so they include things like recreation, like sport fishing, like municipal supply, agricultural supply, among many, many other uses. And so basically what happens is that in the writing of the basin plan or the revising of the basin plan, the water board will go through and say, okay, Alamitos Creek has these beneficial uses. Anderson Reservoir has these beneficial uses, and designate uses for each individual water body. And then after that, water quality objectives are written that are protected or that are intended to be protective of those uses. So in theory, if you meet these water quality objectives, then it'll be safe to conduct that use in the water body. And these objectives are based on a really extensive scientific review process that's done by the water board and by external reviewers. And you can have numeric objectives and narrative objectives. And so numeric objectives are typically a number. And so these can be specific to a certain beneficial use. So for example, cold water habitat and warm water habitat will have different dissolved oxygen objectives. Or you can have the same objective for all the different uses. And so something like that is toxic pollutants. It's not going to matter if you're doing recreation, if there's cold water habitat, or if it's used for supply. We want really low concentrations of toxic pollutants regardless of the use. Then in addition to that, we have these narrative objectives that are a lot more qualitative. So with regard to color, so this is saying water should be free of coloration that causes nuisance or adversely affects beneficial uses. And so you can obviously imagine these are really subjective and they rely on past observations in order to detect a change. And then the last thing that's really key with water quality standards is that there's an anti-degradation policy. And that basically means if something's already good, it can't get worse. And so that's something that we're looking at as well, try to maintain those high quality water bodies. Okay. And so now we have our beneficial uses of the water bodies and we have our water quality objectives. And so now what we need to do is water quality assessment. And this is something that's mandated by the Clean Water Act. It's basically a check-in every 2 years to see if we have good water quality, and if we don't, where don't we have it so we can address it. And so this really relies on water quality monitoring that can be performed by public agencies. So the main ambient water quality monitoring group in the state is the Surface Water Ambient Monitoring Program, and that's a program of the State Water Resources Control Board. And so they're always out collecting data for these basically 2-year report cards that I'll get on to in a second. But then you can also have local agencies, federal agencies, and other collaboratives that are taking water quality data and submitting it to the water boards for review. A lot of the time, you also have nonprofits and community groups that are collecting data. But basically what can happen is that every 2 years, the Regional Water Quality Control Board has to assess all available data to determine the state of our waters in California. And every 2 years, all of these different groups that are collecting water quality data can submit data to them to be included in that evaluation, just so long as they're scientifically defensible. And so every 2 years, the water board will review existing data and put together an integrated report. And the reason it's called an integrated report is because it combines 2 sections of the Clean Water Act. So 305B, which requires states to do water quality inventories and inventories of point source discharges. And then section 303D, which is a list of impaired water bodies. So basically in this report, it's showing what's the state of all of our water bodies and what are the ones that aren't meeting standards that we need to focus on. And then in terms of enforcement, there are a variety of ways that water quality can be enforced. Everything that ends up on the 303D list, so that list of impaired water bodies, is actually slated for developing a total maximum daily load. And basically what a total maximum daily load is it is a regulated amount of a pollutant that a water body can take while still meeting water quality standards. And so these are usually implemented by modifying NPDES permits. So if we find out that for some reason the San Francisco Bay has, high nitrate or something like that, then the way to implement that TMDL for nitrate would basically be to readjust the effluent discharge limits from the wastewater treatment plants or from any industrial discharger. And then another thing to keep in mind is while the Clean Water Act was really designed for point sources, so end of pipe discharges, TMDLs can also exist for non-point sources. So I work on a mercury TMDL, which is actually for mercury and fish in some of our reservoirs. And so obviously fish mercury is not a load and it's not something we can shut off the tap to. And so those are usually enforced actually through non-Clean Water Act means, mostly through the California Water Code. And then another way of enforcing is, so section 301A actually says that you need a permit for any pollutant discharge into any waters of the United States. And the next section, which I'll be going over shortly, I'm going to describe the main permits that are issued under the Clean Water Act. Okay. And so, like I said, the main permits that are issued under the Clean Water Act are our section 402 permits. So that's the National Pollutant Discharge Elimination System designed for point sources. And then we have our section 404 permits, anytime you're going to do a dredge or fill operation in waters of the United States. And then we have section 401 permits, which is a water quality certification and waste discharge requirements for these dredge and fill activities. So you never have one without the other with 401 and 404. And then these section 402 are different. They apply to stormwater, wastewater discharges. So first, I'll go over really briefly NPDES. So like I said earlier, that's the National Pollutant Discharge Elimination System. And it was initially designed for municipal and industrial wastewater dischargers. And basically how that works is that studies are conducted with regards to the current discharge amounts and the concentrations present in the receiving water of all the pollutants. And the water board will develop numeric limitations for effluent concentrations that are discharged from the treatment works. And this requires periodic monitoring and reporting. And if there's an exceedance, then you can get a fine for exceeding that. And then an interesting addition to section 402 has been stormwater, and that has been regulated under NPDES since 1987. And it's really interesting because stormwater was historically seen as a non-point source pollution because it's coming from everywhere. You can't really pinpoint exactly where it's coming from. But the argument was made that once the stormwater goes into the municipal separate sewer system and is discharged out of it, then it becomes a point source. And so now stormwater is managed or is regulated by NPDES as a point source. And the way it's regulated in the Bay Area is by the Municipal Regional Stormwater Permit, which basically sets standards that all of the counties that drain into the Bay have to follow. And the key difference between the stormwater NPDES and the municipal and industrial wastewater NPDES is instead of setting numeric effluent limitations, it's really focused on best management practices to reduce pollutants to the maximum extent practicable. And so that can include things like trash capture devices, things like erosion control, street sweeping, public outreach and monitoring, and construction plans to decrease stormwater runoff. Okay, so next we have our dredge and fill permit. And this is actually administered by the U.S. Army Corps of Engineers, and it applies to waters of the United States. And so this permit is required anytime you're going to remove sediment from water or add sediment to water. And it's basically to protect the water body from any adverse impacts that could occur. And so there's a general permit that's available nationwide if the project's expected to have minimal adverse impacts. But more often than not, we're working through individual permits. And these are for activities that have greater adverse effects to the environment. There's a whole public review process. There's avoidance measures to avoid pollutant introduction. There's minimization measures to basically minimize it when it can't be avoided. And there are also mitigation measures, which are to offset any negative effects you have on a water body. And then moving on to section 404, this is your water quality certification. And like I said, this is required for any activity that's permitted under Clean Water Act section 404. It's administered by the State Water Resources Control Board, and it applies to waters of the state. So there's actually a slightly different jurisdiction between this and section 404 permits, which apply to waters of the United States. There's a little bit difference when it comes to terms of where you're looking at in the actual stream cross section. So if you're working on this, then it's worth knowing those differences. But basically, the gist of this is that the water board has a really broad authority to require mitigation measures and monitoring measures in their jurisdiction. And so we've seen things required under the 401's permits, like monitoring requirements, response plans, different BMPs, and then also measures to protect special status species. And so these are often created through a longer negotiation process with the water board, and they're often project specific. Okay, and before I finish here, I just wanted to let you guys know that the state of water science is constantly evolving, and you should definitely be aware of emerging contaminants that aren't currently regulated, but could be regulated in the future. And these are things that we could potentially see drinking water quality standards for in the future. And we could also potentially see surface water quality objectives for in the future. And so the hot topics in emerging contaminants right now are things like PFAS, per and polyfluoroalkyl substances, microplastics, and certain tire additives that can be toxic to some fish species. And I would say by and large, most of the emerging contaminants nowadays are organic contaminants, so carbon-based. And the common characteristics of them are they're persistent in the environment, so they're really hard to degrade. They last for a really long time. They can be harmful at really, really low concentrations. So parts per trillion, you can see negative effects on organisms. And then another time they can be really difficult to treat. And the positive is that a lot of Bay Area water and wastewater agencies are really getting ahead of the curve with regard to emerging contaminants. And we're already conducting studies and already trying treatment actions even before they become regulated. And so hopefully we'll be able to avoid our legacy pollutants of tomorrow, like the mercury and the PCBs we deal with right now, by addressing these sooner. And so yeah, with that, that was a very quick introduction to both aquatic chemistry and to our main Clean Water Act regulations. And yeah, feel free to reach out to me by email, and I'm happy to take questions if you have them.
Thank you so much, Mark. Any questions, anyone, or comments? We have put into the chat the survey. We want to, excuse me, ask that you complete the survey, and we really want to know your thoughts. And by the way, we will be having another presentation on Thursday morning at 10 relative to plastics and water. So we want to invite you to sign up for that if you're interested as well. You can just unmute yourself if you have a question for Mark and ask it, or you can put it into the chat. We have a question here, Mark. Which water contaminant is most concerning?
Ooh, that's a really tough one. For me at the moment, the things that are most concerning are the things that we know the least about. And I'm particularly concerned with these persistent organic pollutants because we're just now learning what the health effects could be and the ecological effects can be. And in a lot of ways, it's kind of too late because they're already present in the environment. And so, yeah, I'm really concerned with these persistent organic pollutants that, like PFAS, for example, that can just stay in our environment for millennia and that won't be degraded naturally. And so that kind of requires us to get ahead of the curve on those and start addressing the source of those as opposed to the treatment. So trying to cut production of those.
Okay, thank you, Mark. I got a question for those that are here. Is there a takeaway? What one thing that you're taking away from this presentation? You can type it in the chat or just unmute yourself. All right, anyone? A question here, Mark. Who determines the list of contaminants for the UCMR program?
Yeah, so the State Water Resources Control Board is the primary agency that's dealing with regulated and unregulated contaminants at the moment.
Great. All right, please complete the survey and that we put into the chat link. We just did it again. And we will also send you the survey link via email as well. But we really want to know your thoughts. And we're trying to advance our industry in multiple ways. So there's a lot of thank yous coming through, Mark. And thanks again for your great presentation and sharing your time and your experience and your knowledge with everyone. Someone put here that my takeaway is that water is so simple, yet various components and how they relate is complicated. Thanks for the presentation. That's wonderful.
Awesome. Yeah, thanks for having me and thanks everyone for coming.
Thank you, everyone. We still have 2 presentations today in the afternoon and also Wednesday and Thursday, 4 presentations on each day. If you haven't signed up already, please do if you see something of interest. And we look forward to continuing to move our industry forward and sharing knowledge and information. Have a great rest of your day and hopefully you have a great lunch. We'll see you soon. Take care, everyone.
Thank you.